All right, how am I doing volume-wise for everyone? Good? All right, great. Well, thank you very much for giving me the opportunity to speak to you today. So great big thanks to Dawn and Jeff and Ellen for all the hard work they've put into organizing this fantastic workshop. It's really great to be here. I'm going to disrupt their mode a little bit with this lecture and ask that you please interrupt me. I will repeat the questions. I'll do it. I'll do it. Because this is really directed at learning. This is supposed to be didactic and pedagogical, so if you have no idea what I'm talking about, there is absolutely no point in me continuing to talk. I don't need to hear it myself. And what I want to talk to you about today is planet formation by gravitational instability, and you will see here that I have put a question mark at the end because I'm not so sure it's really a very useful paradigm to consider for the bulk of planets. I'll just make one quick side note, is that what this talk is going to focus on is gravitational instability of the gas disk. Now, Andrew and Richard yesterday both mentioned that you can get, and Doug just now mentioned that you can get gravitational instability in the layer of solids, the planetesimals. And that's an entirely different thing that has to do with the formation of planetesimals. When people say planet formation by gravitational instability, they really mean something happening on a larger scale, a sort of top-down method of forming planets. So, all right. I'm going to start out with sort of a high-level bottom line, and then I'm going to walk you through the steps slowly. So first off, I'd say that if I were to summarize what this talk is about, I'd say that in general, very few disks that we observe appear to be massive enough to undergo gravitational instability and fragmentation, except at very early times, which I would argue are not ideal for forming planets. Those that do end up fragmenting to produce something are more likely to produce brown dwarfs or even M-stars than they are to produce things that are planets. And finally, there's sort of a newer paradigm where people consider not just the sort of first step of fragmenting out of the gas these large things, but then take into account the fact that they will then move through the disk via migration, which Doug pointed out is extremely important for all types of planets, and that this migration process can lead to interesting effects like tidal disruption. But I'll show that in the case of gravitational instability-borne fragments, this often leads to complete disruption rather than just a little bit of downsizing and mass reduction, although there may be some assistance provided to the formation of solid cores by this. And on a side note, I want to just bring something that I think is really important to your attention, even though this is maybe a bit pedantic. But the study of accretion disks was really born thinking about galactic dynamics, maybe AGN disks, or the disks around X-ray binaries. And this has really colored the way that we look at accretion disk dynamics. Much like many of our theories of planet formation began trying to explain the solar system, right? We had this really nice model. There's the terrestrial planets, the gas giants, the ice giants, and for many years, we thought all exoplanetary systems should form that way, and that sort of restricted our thinking. In the same way, the thinking about how gravitational instability works has been sort of torn and turned by this emphasis on other types of accretion disks. And the two main differences between those other types of accretion disks and the ones we're talking about today are that, first of all, the thermodynamics of protostellar and protoplanetary disks, where gravitational instability is going to be important, are dominated by stellar irradiation. And that means they're going to behave a little bit differently than some of these other types of disks. And I'll talk in a lot more detail about this in a minute. And the second thing I want to highlight is that protostellar and protoplanetary disks that are, again, likely to experience gravitational instabilities do not have H, the scale height, much, much less than R. So the aspect ratio is not extremely small. It's sort of a little bit less than 1. And that, again, changes the behavior of the system. So let's look at how. I'll just highlight a few important terms that I'm going to use, because, again, I think it's very good to be clear about what we're saying. So what is self-gravity? Self-gravity is just sort of the self-attraction of gas in competition with the central body. So gas in a disk is going to feel gravity from the star, but it's also, if there's enough of it, going to feel the gravity from the gas next to it. gravitational instability is a linear hydrodynamic instability that can arise in a self-gravitating disk of gas, particles, or both. Okay, the next thing is a fragment, which is not gravitational instability. Fragmentation, gravitational instability are not one and the same thing. Fragmentation, or a fragment, is a marginally bound gas clump that forms as the non-linear outcome of gravitational instability. Gravitational instability is just a linear instability. If it goes non-linear, that's when fragmentation happens. And then, of course, there's planets. And I'll talk about this more this afternoon, but what a planet is, that really depends on whom you ask. And when you start talking about these alternative modes for forming planets, your definition begins to matter in whether or not you think they actually form. So, what is gravitational instability? Most simply, I said it was a hydrodynamic instability, and the basic idea is that you have a disk. Is there a laser pointer on this thing too, or no, it's a separate one? Gotta do two hands here. All right, so you have a star, you have a disk, and the competing forces are pressure, which is trying to puff the disk up, gravity from both the star, and then self-gravity can operate in the vertical direction, is trying to compact the disk, and then of course there's that Keplerian shear, which is stretching things apart. So gravitational instability becomes important and arises when the local self-gravitational force overcomes pressure support on small scales and shear support on large scales. And the standard way this is expressed is in terms of 2 raised q, where it's the sound speed times, this is actually technically the epicyclic frequency, but in a Keplerian disk that's the same thing as omega, over pi g times the surface density sigma. And as Richard noted yesterday, it is often very convenient to rewrite this as some numerical fudge factor times the stellar mass over the disk mass times the aspect ratio h over r. So, can anyone tell me why there's a numerical fudge factor, or maybe what are the ingredients we need to go between these two? Does everyone know how we get between these two? Is that obvious? What's one equation that I haven't written on the board that I need to go between q being cs omega over pi g sigma to m star over m disk h over r?
H equal to cs over omega.
H equals cs over omega. Great. Okay, we've got one. All right, and that's basically coming from the fact that you have the Keplerian velocity worked in here, and that's how you get that. So that's going to help us get the h over r. We've got one more thing we need to replace. We got to get from a sigma to what? What else is in there?
Density.
Thank you, density. All right, okay, so, all right. Anybody else, can you tell me why there's a fudge factor? Why is it not a one-to-one relationship going between sigma and the mass of the disk? Surface density profile, right. So that F factor comes in because you have to say sigma is equal to some constant, sigma naught, times, we usually say it's some power law to some power. Okay, I'll call that F. It's not exactly that F, but it's related to it. Okay, so that's how we go between those two. So depending on how you think your disk is structured, maybe it has an exponential decay, there can be a few deviations there, but that's the basic idea. So this is really where many people stop when they think about gravitational instability, but in fact, this whole paradigm, this whole relationship is really only accurate when we're in that special regime that H is much, much less than R. That is the regime in which this dispersion relation, which is where this Q comes from when M, which is the mode number, so it's the M equals 0 mode, which is the axisymmetric mode. That's where this relationship comes from. So this sort of standard description that you are familiar with only applies in that local approximation and technically only applies for axisymmetric modes. So what happens if we relax that assumption? We say, well, what about those other disks, the one who are not very, very thin or very, very cold, when H is just a little bit less than R? This is not something new. This is from a paper by Lau and Bertin in 1978. This is the dispersion relationship which governs the growth of gravitational instability in a disk which is not very thin. You can see it's more complicated. It depends on this extra factor here, which is basically a function of the disk mass compared to the stellar mass. And similarly, because of that relationship on the previous page, right, that there's this correlation between M star and M disk and H over R, when we're talking about Q being of order unity, then the disk is going to be fatter. And it turns out that the growth of the gravitational instability begins at slightly higher values of this parameter Q. So it doesn't happen at the same time. It doesn't start to grow for exactly the same types of parameters if the disk is kind of thick as compared to the disk being kind of thin. Or alternatively, if the disk has a lot of mass compared to the central star, maybe 0.2, 0.3 times the mass of the central star, or just a little bit, 0.01 times the mass of the central star. And if we look at this in a slightly prettier way by looking at nice pictures, we can see that the morphology of gravitational instability looks different in these two cases. So if you were talking about the local regime where H over R is maybe 0.01 or even 0.1, this is kind of the transition, you see there's these tightly wound spirals here, and this is a shearing sheet simulation from Charles Gammie in 2001, and that's just boosting into that local frame that both Andrew and I think Richard talked about yesterday, so we can study very, very small scale behavior. On the other hand, if you allow the disk mass to become large or H over R to become somewhat larger, then the morphology changes. Instead of having these high M, so many, many spiral arms, you have these lower M modes, and the disks look very different. And again, this isn't some fuzzy math I'm doing here. This is clearly drawn from the dispersion relationship. So this is again from that Lau and Bertin paper. So this is Q squared, and this is the dominant wavelength on which the instability grows. And again, J is basically how local or global we are, whether or not it's a low disk mass or a high disk mass when Q equals 1. So you can see that two things happen. First of all, we get growth. The disk is unstable at higher values of Q as J becomes larger, and that the wavelengths, lambda, over which the instability grows also become wider. So we can get growth at higher values of this critical tomb ray parameter, and we can get growth on a different and a larger range of scales. So again, global versus local, it's not just some little thing we need to worry about. The nature of the instability fundamentally changes. Okay, so what are the implications of this? I've just talked about the dispersion relationships and therefore the linear phase of the instability. But if we're thinking about planet formation, then we end up wanting to understand the nonlinear phase. And nonlinear is what happens if the instability doesn't saturate, right? Richard talked about co-rotation torques saturating. This is the same sort of idea. If there's some other process that turns off an instability, it saturates, you won't get fragmentation. When we're talking about gravitational instability, there are two ways that it can saturate, either by mode-mode coupling between spiral arms or by thermal feedback. And these can both operate in both of those sort of local and global regimes that I just mentioned, although more often than not, this happens in the sort of global regime and this happens in the local regime. So let's look at what this means in a little bit more detail. So mode-mode coupling, what you're seeing here is a plot from a paper by Laughlin, Korchagin, and Adams in 1996, and there's dimensionless time on the x-axis and the amplitude of the strength of a given spiral mode on the y-axis. So you can essentially think about this as saying, okay, if I look at these pictures, here I'd say, okay, there's a lot of power in maybe m equals 2. This one, probably mostly m equals 2, but it's a little bit off center, so maybe there's even some m equals 1. Whereas if I were to ask how much power is in these two, I'd say, oh, well, that's a much higher m, maybe 5, 6, 7. So that's what all that means. So what they found was when they did these simulations of these global gravitationally unstable disks, they found that the instabilities didn't keep growing sort of to infinite densities. Those spiral arms didn't just keep contracting to infinite densities because there was coupling between these modes. And so as maybe the m equals 1 mode and this is the m equals 4 mode grow, they suppress the further growth in the m equals 1 and the m equals 2, and the strength changes off between these things. And essentially as a result of that, you don't get the spiral arms sort of growing to infinite density, and they do what Richard mentioned yesterday, which is transport angular momentum. And so the instability kicks in, these spiral modes start to grow, they transport angular momentum. By transporting angular momentum, mass goes in, which means the surface density goes down, which means Q goes a little bit up. And so it's not a runaway process. And so this transport can be very important in those parts of the disk where maybe the magnetorotational instability or magnetized disk winds are less important. And what you can think about this is that if this mode-mode coupling prevents the runaway contraction of those density peaks in the spiral arms, that means that locally the surface density may never be high enough for that self-gravity to win out over pressure and shear, which is fundamentally what we're talking about. And so you don't get that nonlinear evolution. It just kind of stops. The second one, the second way that you can turn off gravitational instability or regulate gravitational instability is by thermal feedback. And this is the one that if you've heard about gravitational instability, you've probably already heard about. And I've chosen to mention it second because it turns out that for protostellar disks, this is often not the most important criterion, although it's physically totally correct. And the idea here is that when you have those spiral modes, whether or not they're large scale or whether or not they're small scale, they're essentially shocks, and they're subsonic shocks which dissipate energy in the disk. And of course, when you dissipate that energy, it heats the gas up, right? Well, 2m raised q is a balance between pressure, surface density, and shear. So if those shocks dissipate, the gas heats up, the pressure gets bigger. And so whether or not those shocks can sort of turn off or saturate the instability or allow fragmentation to proceed, that depends on how quickly the disk can get rid of that heat. So you have a shock. If the disk can get rid of that heat very, very quickly, then the pressure is not going to go up, the instability is going to keep growing, and you will ultimately get fragmentation. If, on the other hand, when those shocks dissipate, you heat up the gas faster than it can get rid of that excess energy, then eventually the surface density will, the temperature will go up a little bit, Q will go up a little bit, the instability will weaken, and you can get into this self-regulated feedback cycle where the disk starts to cool down, it becomes a little bit unstable, it stirs itself up, it heats up, and it comes back up. And you sort of regulate to this saturated level of the instability where you don't get runaway growth to fragmentation. And this is often expressed as this cooling time criterion, which Richard mentioned yesterday, where there's the cooling time. This is basically, right, this is the energy in the disk and how long it takes to radiate it away, sigma t to the fourth. And there's a factor here that can be very important, which is the opacity, so how quickly you can diffuse energy out of the disk. And it's often parametrized as some number times the disk dynamical time. And that's a natural parameterization, right? The instability grows on the disk dynamical time. So clearly, if you want to either understand if the disk heats up a lot or cools down a lot, you also want to know how that behavior happens on the dynamical timescale. Yes? So actually, what I would argue is that the difference, this is an approximation side. So the question is about whether or not there should be an explicit expression of the disk scale height in here, because that's going to govern how it cools. So that comes in the difference between this being an equal sign and an approximation. So some of that is built into the optical depth, which obviously depends on how much mass you have to go through to get out of the mid-plane of the disk to cool off. But you can also, there's basically different numerical coefficients and different factors of gamma of whether or not you consider 2D, the radiation in 2D, or if you ask what happens if I have a perturbation at the midplane and allow that to cool off. And you can work it out, and it turns out it's just gammas and order unity coefficients. Anyone else want to be brave like Smadar? I guess it doesn't count if she's brave. Okay, so cooling time. Great, nice parameterization. Physically, this is determined by the opacity of dust. And so I would say there be dragons here, because now you have to worry about all of the grain growth discussions we had in both Jenny's talk and Andrew's talk, because that's fundamentally going to determine how you cool. It also depends on the equation of state of the gas. And I would say that for protoplanetary and protostellar disks, where gamma is 7/5, the literature consensus is that it's probably somewhere between 8 and 15, that critical number beta. Numerical modeling is required because, again, this is all about the non-linear phase of the instability. We cannot write down an equation that tells us the answer. There has been much work on determining exactly what this number is in the literature. I'm not going to spend time on that today. For our purposes, it doesn't really matter if it's 8, 10, or 16.8. They're all of the same order of magnitude. And we'll see when we look at actual protoplanetary and protostellar disks that the difference between these two numbers isn't super important. Okay, so again, looking at all that in pictures as opposed to in words, this is what the sort of saturated phase of the instability looks like with this mode-mode coupling or thermal feedback, which is often referred to as gravitoturbulence when it's on these small scales. And then, alternatively, this is sort of the other option, which is that you get the nonlinear growth and you end up getting fragmentation into these bound clumps. So that's the basic physics of how we go from self-gravitating disks to gravitational instability to nonlinear growth and fragmentation. So that's the basic physics. Now let's look at the state of the disks that we're talking about. What do protoplanetary and protostellar disks look like around solar-type stars? So we need to understand this because we want to understand where we fall, what kind of physics do we need to worry about. So what I'm showing here is a contour plot as a function of the accretion rate going through the disk, m dot in log, as compared to the radius in the disk. And I've taken a massive protostellar disk around a sun-like star. So the disk-to-star mass ratio is about 25%, is a solar-type star, and I've said, the radii of these disks seem to be about 100 AU. I'll note that this is quite massive for disks that we observe. It's true that there are many uncertainties in the masses of the disks, so I don't think this is implausible, but it's definitely at the upper end. So the contours here are showing temperature. And the temperature is being solved with this equation, which is basically relating the temperature in the midplane to the amount of energy that is dissipated by accretion at some rate, so 10 to the minus 9, 10 to the minus 8, 10 to the minus 7 solar masses per year, where there's a relationship between the accretion rate and how much energy you put into the disk. And you can think of that either in the context of these alpha models that Richard mentioned, or even more simply, if you have material in the disk and you want to move it inwards, it had to get rid of some energy to do that. And that energy is going to go into heating the disk, at least some fraction of it. So that's one component of the energy. And then there are these two other components, one that has to do with heating due to the central star, and one that you could put in having to do with heating due to some external background radiation if, for example, you're living in a star cluster. What we find is that if we take a standard pre-main sequence model for the sun, look at, say, Barof's 2015 models, which tell you how bright a star is as a function of time, how big it is, and how big it is matters because we have to worry about the accretion luminosity in addition to its sort of contraction or our hydrogen burning luminosity. And if we calculate the temperature in the disk, including these other irradiation terms in black, versus the temperature if we were to just consider the dissipation of accretion energy in white, you can see that the curves do not match up. And in particular, in the outer parts of the disk, beyond, say, 30 AU, the temperature is dominated by the stellar irradiation. Now, this may seem counterintuitive, right? The star is getting further and further away. How is it possibly having a larger and larger effect? Well, you can work out what this the scaling of the sort of flux of stellar radiation is as a function of radius, and it falls off less steeply than the accretion luminosity, which has an omega squared in it, which gives you an r cubed in your denominator. And so it turns out that radiation actually becomes more important compared to the dissipation of accretion energy as you go further out. So this is what the temperature structure looks like. And if we then translate that into 2 raised q, and that cooling time, what do we find? So the black lines in the contours show you the value of 2 raised q, and you can see this is 2 here, and this is 1. So for my very massive disk, the most outer regions are indeed marginally gravitationally unstable. So you might expect instabilities to grow, although we'll certainly be in the local regime, not in the local regime, in the global regime. And you can also see these are the critical cooling times, and I said, our sort of the magic number is probably of order 10, somewhere between 7 and something 14. And you can see that we're well into the regime where the disk is quickly cooling by the time it's gravitationally unstable. So if I take the parameters for a massive protostellar disk where Q is likely to be low enough that gravitational instability matters, cooling times are always going to be short. So I can either saturate my instability by mode-mode coupling, because I can't do it by thermal feedback, that's possible, or I'm going to fragment. Those are sort of the two options for a disk like this. Now, this was a pretty exaggerated, massive protostellar disk. It's the kind of thing we might expect to find very, very early on in the star formation process. What about a more normal class 1 or class 2 disk of the type that Jenny discussed yesterday? So now instead of taking a very, very large mass ratio, let's say it's only a few percent. This is sort of the classic case we consider. And again, about 100 AU. This is the same plot with radius on the x, accretion rate on the y-axis where I'm calculating the temperature. And you can see that, again, the temperature due to irradiation dominates. And now if we go and look at this plot of Q and the cooling time, there's no part of this disk which is anywhere near a 2 raised Q value of 1. The disk is just not gravitationally unstable. And it's not gravitationally unstable because it is being very well heated by the central star. And again, this is one of those fundamental differences between the sort of evolution of these models, which came about for, say, AGN disks or CV disks, where these white curves that tell you how much energy is being dissipated by the accretion governed the evolution of the disk. For protostellar and protoplanetary disks, the star is just too strong, and the star really dominates the thermodynamic behavior. And so this is why it can be very challenging to get gravitationally unstable disks which will nonlinearly saturate and fragment in the types of disks that we observe around young stars. So this is the state of the disks. I've said, okay, if I take some typical numbers, masses, radii, stellar properties, what state is the disk in? But there's one other thing we have to worry about, which is, how did we get here? So Richard mentioned yesterday that disks are not these isolated things that came down from on high and live, away from other stars, or in fact the star-forming core out of which they were born, right? They're part of the star formation process. They're having material come down on them. They're angular momentum transport machines. They take material from the large scales and they move it to the small scales. So we have to consider what kind of environment they're in. So let's say I have a disk with Q just a little bit bigger than 1, and I want to make it gravitationally unstable. What are my two options? What are two things? What's one thing I could do to make my disk more unstable?
Lower the temperature, make it more massive.
All right, I've got both. I can cool the temperature or make it more massive. So I can add more mass with my teapot, raise the surface density, which is going to drop to Q, or I can cool the disk down by pouring ice cubes onto it. No, how am I going to cool the disk down? What's determining the temperature in the disk? The opacity. Okay, so I could magically reduce the opacity. What else can I do? I can put sunglasses on, right? Those are basically the two options, and this is why understanding how the disk gets to this state is very, very important, right? It's very easy to expect that I'm going to add mass to my disk because they're in this environment where they're accretion disks. They're taking material from large scales, they're channeling them down to the star. That's what they're going to do. They're going to get mass. But because the feedback loop between how quickly I'm moving mass through the disk and how much energy I'm dissipating, that thermal feedback loop, because that doesn't work very well, because the star is so important, it can be very hard to make this sort of ice cube analogy and just cool the disk down rapidly. And so this is one of the big challenges in getting disks that are likely to make planets, because it's only under very, very limited circumstances that you can make the disk reach this unstable state by cooling. So a sharp opacity transition or disk shadowing due to some inner wall or maybe warping, those are all possibilities. But now we're starting to get into this kind of fine-tuning part of the parameter space, and we should start to worry a little bit. I'm getting close on time, Jeff, I think. So, okay, I'm going to 5 minutes. All right, so keep this in mind because this is going to be very important as we start to try to understand if we get to the state where we make fragments in the first place, what they're going to be. So it turns out you can nicely divide parameter space just by considering accretion rates, but I'm going to skip past this in favor of some things that are a little bit simpler and just ask, okay, we went through the fact that it's kind of hard to get the right initial conditions, but let's say you do have those initial conditions where your disk is unstable and you can't saturate your instability and you're going to fragment. What are those fragments going to be? So this is the 0th order picture. Recall the isolation mass. This is the idea that if you put a secondary potential in your disk, there's only some amount of mass it can grab up away from the central star. That's sort of the maximum amount of mass it's going to be able to get at some level. And you can nicely express the ratio of the isolation mass to the stellar mass as a function of 2 raised q and the disk aspect ratio. And let's come over here to our solar system, where Q maybe was 20 or 30, and we think at the time of gas giant formation it was probably pretty thin. And what do you know? The contour of isolation mass is not very different from Jupiter, which is about 10 to the minus 3. If we crank Q down to a disk that is self-gravitating, and we say, well, wait a minute, we know that our disks weren't self-gravitating when h over r was very small, all of a sudden we climb up this contour and our isolation mass is a star. So this should be our first clue that something is going to be problematic if we want to make planets out of fragmentation, because our sort of standard mass scale is a brown dwarf or probably actually a star. So what makes matters worse is that if the disk is driven unstable by infall, it's even harder to avoid growing to this mass. And again, simple order of magnitude way of understanding this is you take a disk and you add mass to it, you drive it gravitationally unstable, you make a fragment, that fragment has a Hill radius, and now you keep adding mass, and the disk is going to grow. Because if we take everything we know about star formation, we find that as the star forms, the material that you sweep up from the molecular core typically has higher and higher angular momentum as a function of time because you're drawing from larger and larger scales. And that material has too much angular momentum to land on the star, right? It lands in a disk, and it lands outside of where the previous material landed. So now you have more and more material piling up outside of your secondary, which has a Hill radius. So unless you have a very, very clean gap initially, which is hard in these messy, turbulent disks, basically all that material, if it's going to get onto the star, has to somehow magically hop over the planet. That doesn't happen. So it's very challenging to prevent some of this growth. So that's the 0th order picture. Things can be a little bit more complicated, and I'll spend a lot more time on this in my next talk this afternoon. But I'll just start out by saying, okay, those were the sort of upper limits. But in general, the initial masses are going to be some numerical factor times the surface density times the scale height squared, because that's the wavelength on which the instability grows. And so this is radius in the disk, and this is mass of the initial fragment formed. And these are basically different numerical factors put in front of sigma h squared. And you can read any of these papers to tell you how they derive them. Again, this is the nonlinear part of the instability, so I think we probably don't know what it is to order of magnitude. But just take a look at these numbers. Even the lowest estimate on here, we're still looking like we're starting out with planets that are a few Jupiter masses. And then if we add in the fact that there are these other masses, which I just sort of mentioned, gap opening or isolation mass to which they might grow, we should start to be very concerned about whether or not these things are going to look anything like the planets that we observe. And so I will just say that you can think of gravitational instability as a little bit like a choose-your-own-adventure, and you can sort of ask, well, if I follow these tracks, what kind of outcome am I going to end up with? So if I say, well, I'm a global disk, and let's see if I'm slowly cooling, well, then I'm probably going to look like a compact class 0 object, and probably I'm going to suffer from mode-mode coupling, and that's going to saturate me, and I'm not going to fragment. If I cool fast, yeah, you're going to fragment, but then you have to start to worry about these mass issues I mentioned where you're this big, massive global disk, and it's hard to prevent long-term growth. What about the local regime? If you're cooling fast, great. You might fragment at those extreme mass ratios, and maybe you're a shadowed protoplanetary disk, you've somehow managed to cool, but more likely if you chose this adventure, you're an AGN disk. Same thing goes if you're in this local regime and you're cooling slowly. Yeah, you can get this self-regulated GI, but probably you're an AGN. So I will just put up this slide as a teaser for the talk this afternoon, where I'll talk in a lot more detail about all the things that can happen after you fragment and how that might relate to other modes for accretion at wide separations. Thanks. So the question is about whether or not what we'd call a locally isothermal approximation, whether or not that's a reasonable thing to do. And locally isothermal means that the temperature doesn't change, but it's a function of location in the disk.
Yeah, like what do you think, like how consistent
Right.
is it to start with an isothermal?
So I think that ironically, even though anyone who's ever done a simulation has been yelled at for doing isothermal, it's actually not bad for this context. And the reason is because of these cooling times. So if you look at, let's go back to the disk that's unstable. If you look at the disk that's unstable, right, when Q is near 1, the cooling time is very fast. A cooling time being very fast means that the effective equation of state is much more like an isothermal disk than an adiabatic disk. If the temperature is being set by the star, then that's much like a locally isothermal disk where the temperature is just a function of your distance from the star. It doesn't matter about the internal dynamics. It's not a perfect approximation. If you wanted to follow the nonlinear phase, then you run into real problems. But for the onset, I think it's remarkably good considering how simple it is. Yeah, so the slide I skipped over. So the question is about how the fact that the disk is not isolated influences whether or not it's gravitationally unstable. And
specifically, if you have any thoughts about gravitational instability in those, coming in material.
right, so is the material coming in somehow unstable or triggering instabilities? So I'd say the material coming in from the core is gravitationally unstable in the sort of gene sense that it's obviously not pressure supported, so it's coming down. It's probably turbulent. And the rate at which material comes into these disks is actually pretty important for setting the evolution. And so what this plot is showing you, just ignore the y-axis, on the x-axis is understanding how the disk behaves as a function of how quickly you add that material to the disk. And if you add it in kind of slow, you end up getting sort of this marginal growth of the instability, and if you add it in really fast, you trigger an instability. The thing is, when you trigger instability this way, you always end up in this sort of global case. And so this is probably something that might happen at very early times. Maybe we haven't observed this yet because these are very, very deeply embedded. But even if you fragment at these stages, your mass scales are going to be pretty big to be planets. And also, if you imagine that you're going to keep accreting the rest of your stellar mass, if this happens early, it's very hard to keep something and not have it fall into the star along with the rest of the material.